All right, so we just finished that series with Ted walking us through the reinforcement learning book. And so what we'll do today is we'll look at some of the state-of-the-art stuff that's been going on at DeepMind. Specifically, we'll be looking at all this stuff related to Go that they've been working on. So they have this AlphaGo um, algorithm. And so we'll look through the details and kind of the evolution of what they've been working on with that. For anyone new here, this is a San Diego machine learning group. We have all kinds of different sessions. We just finished one that was a book club, and we also do one that's after this that is all about project collaboration. I'm Ryan, I'm one of the organizers, and then the other one is Ted. So getting into this, I'll start just kind of looking at the problem that they were trying to solve. So they were looking specifically at the game of Go to start, and this is kind of an interesting one because it has such a large complexity in comparison to even chess and other games like that. It's so complex that many people thought that maybe a computer can just never reach human level performance, where if they can, maybe it's a decade plus away because it has so many different branching factors that you just end up with so many possibilities. You can't do any of our traditional algorithms to try and find some sort of optimal playing strategy. And so looking at a little bit at the game and the complexity, it's got a 19 by 19 board. So this is even bigger than chess, even bigger than a lot of the other games that we're used to. And you can place a piece on pretty much anywhere on the board. And so this makes it so that there's tons and tons of different options, and the games also go very deep. So there's lots of options at any given turn, and then there can be many turns up to like 200-ish. And so you can have tons and tons of different things that can happen within a game. And so you can't really have some sort of simple strategy. You have to think about it pretty deeply. And so using other algorithms, you go apply it to this problem and you just say, okay, it's going to take me a year just to figure out the first move or something like that. And so all of this process is about figuring out, how do we find good moves more quickly? How do we develop a strategy that extends into the future? And all kinds of stuff like that related to the game. I see a chat in here. The board is that board is 18 by 18. I'm not sure. I just am going, I have very limited Go knowledge actually. So I am just going off of what the paper said. Looking at the sequence of papers from DeepMind, they've done more beyond this, but these are the ones that we'll be covering today. So the first one is AlphaGo, and this is kind of their proof of concept showing we can actually solve this game and we can get very good performance, superhuman level performance. But along with this, they had to do a lot of custom things specific to the game in order to make that happen. And so the next evolution beyond that is AlphaGo Zero. And what they were trying to do is stripping away a lot of those custom things that made it work and say, can we generalize this and make it so it isn't reliant on prior knowledge? It will work on other games. And they're trying to just simplify it. And so the highlight of that one is tabula rasa. It just learns from itself. It learns from nothing. So this, I'll talk about these in more detail. I won't go into too much depth now. And then the next evolution beyond that is AlphaZero, which they basically took the AlphaGo Zero, and then they just said, let's apply it to other games and let's study it a bit and let's make sure that we've got a algorithm that can be applied to other similar games and make sure that we haven't done something in order to only make it work for Go. It also works for other games and can create very good performance. So starting off with AlphaGo, it has a whole bunch of different networks and it's very complex. So I'll start by just running through the various different networks, and then after that, I'll discuss how exactly they're pieced together and what they all do. So we have the rollout policy network, and we have the supervised learning policy network, we have the reinforcement learning policy network, and we have the value network. So we have 4 different networks that we're working with. And this is the diagram that they show, and I'll kind of walk through what all of these individually mean in the later slides. So the first one is the rollout policy network. And so what this network does is it essentially tries to give decent move recommendations, and it tries to be very simple and very fast. So you've got a certain board state, it takes in that board state, or rather it takes some simplified features. So these features in the bottom corner, they basically, if you look at traditional Go engines, they'll look at various features. And I don't fully understand them because I don't know a ton about the game of Go, but basically they've derived certain patterns and they've said, okay, when you see this, that means something. And so you give those pattern features to this network, and what this network does is it just tries to say, what are the probabilities that a pro player made this move? And so there's this KGS Go database that has 30 million games from these professionals. So they've played all these games, and basically this simple network is just trying to say, given this state, what would a pro play? What stone would they place next? And so this simple network is able to get that 24.2% of the time, which is actually pretty good when you consider 19 by 19 is, I don't know, a little under 400 possibilities. So it's significantly outperforming just random guessing. And one of the big benefits of doing this in such a simple way, just taking in these pattern features, and then they're literally just doing a linear layer, a single one. And it's not doing anything fancy, it's not a deep network, but it allows them to make a decision in 2 microseconds. And we'll understand why that speed is so important in the later slides.
By the way, Ryan,
Mm-hmm.
Just a little bit of trivia in case people were wondering. The term rollout came from TD Gammon, where basically they were trying to play backgammon, and so what they said is, well, if I make this move, what is likely to kind of happen from there on out the rest of the game, right? You're deciding your next move, but to evaluate it, you might just sort of say what happens after that. And they needed something fairly reasonable to say what's a likely thing that's going to keep happening. But in that case, with backgammon, you roll dice and then the moves happen. And so that's why they called it rolling out the next set of turns. So that's where the term rollout came from.
I didn't know that. Interesting.
Yeah, so rollout generally means like it's the thing you're going to use as sort of like the default when you're not actually specifically learning. If you just want to say like, if I do this, what was my opponent going to do? You could use the rollout policy. And it's like, oh, well, they're going to do this. And they're going to capture a bazillion of your pieces. Well, then the rollout can figure out that the opponent can capture, a bunch of your stuff next turn, then that's probably a really, really bad move because the rollout's not even that smart.
Yeah. So the next network in the series, it works similarly to the rollout policy network, but it has a different input representation. So the rollout network, it had those simple features that were just based on some patterns. And what this one does is it looks at the actual raw board state and a little bit of the history. So it knows what moves were made previously and what the previous board states were. And so this one is a much more complicated convolutional neural network. And that's what this diagram on the right shows, is basically you have this state, this is showing where the stones have been placed. And then you have the convolutional neural network that goes through multiple layers of looking at sort of the local patterns. And then from there, it outputs a probability for every spot on the board saying, I think 60% this is where a pro would play, 10% this is where a pro would play, 5% this is where a pro would play, etc. So it's just trying to predict what a pro would do. And it's way, way, way better than the rollout network, because the rollout network's goal is just to be simple and fast. This one is actually trying to be more correct and be able to predict what a pro will play. So this one takes 2 milliseconds, which is massively slower than the rollout network. The other one is 3 microseconds. And so this one is way more accurate in turn, though. It's able to get 57% accuracy using a combinations of features and board position, or 55.7 using just the board position. So it's significantly better at predicting what a pro is going to do.
Hey, Ryan, quick question. The 48, so the 19 by 19 by 48, does that mean there were 48 features for each position?
Yeah. And they didn't really go in too much detail in the paper, but I have to assume that's a certain length of history and a certain length of these additional features that they're talking about. They didn't really go into detail about that. But one of the things that they did mention is one of these features potentially is just a single binary 19 by 19 saying black is playing, white is playing, etc. So there's other stuff stacked in there that doesn't really have like spatial information. It's just put in this format so that it can be kind of combined with everything else. So yeah. the 48, I would have to look into more detail of what that exactly is, but I know there's other stuff packed in there.
Okay, got it. Thank you.
Yeah.
Hey, Ryan, do you know why they're using CNN rather than just a regular DNN?
So a big part of that is just computational complexity. So a CNN can look at a 19 by 19 by 48 pretty easily. And a DNN would probably be significantly more expensive. But on top of that, we know that we do actually care a lot about these spatial patterns. So the CNN can kind of inject that knowledge that we know that pieces close to each other are important. And with a sufficiently deep network like 15, you can even look at patterns all the way across the board. So you don't really have to be concerned with, they also, so one of the things about Go specifically is there's symmetry. So you can rotate the board or you can flip the board. And so they also exploit that a little bit in their training procedure. While they're training, they do rotations and flips and stuff like that. And that wouldn't work with the DNN because it would just know statically their positions. So there's a few different reasons that they chose CNNs there.
Yeah, thanks.
And so after that, there's the reinforcement learning policy network. And this is exactly the same shape, the exact same input, the exact same output as the previous network. And it's just copied the same parameters as the previous one. So you train a model to predict what a pro player would do. And then you go plug it into this reinforcement learning framework and you play it against itself. And you try to make it improve. And so now its objective is to actually improve its win rate against itself. Because before, it's just trying to copy pro moves, which will probably make it do something reasonable. But if you want it to improve beyond that, you need to actually do some aspect of self-play. And then it might no longer do what a pro would do, but it might make even better moves and it might be able to win. And so they use this policy gradient, specifically reinforce. Ted mentioned this a while ago, but I don't have time to really go into the details, and it's not really the contribution of the paper. This is just what they chose to use here. But basically, they pit the network against itself. It plays a whole bunch of games. It tries to improve. And then after that, they pitted the original supervised learning policy network against this reinforcement learning network, and it was able to win 80% of the time. So it did actually move in the correct direction and learn to make moves that caused it to win rather than just imitate pros. And then after that, we have the value network. And this is very similar to the previous networks. It's got the same input representation. It's got the same underlying CNN architecture, But what this one is trying to do is it's just trying to predict whether a current position is winning or not. So it looks at this board state, it goes through the CNN, and then its final output basically is what do I think my win rate is here? So if it looks at a good board position and it sees that it's a few points up, it says, I think this is a promising position. I think there's 90% chance I win here, for example. And so what this model is doing is it's looking at historical games and it looks at a position and then it says, am I going to win from here or not? And so this whole thing is just focused on evaluating the quality of its current position. And we'll see why this is a valuable additional step in later slides. And so one of the things that they ran into is this big leakage problem, because they were looking at this KGS Go database and they trained the model on all the different positions, and then they realized actually that's not so great to do, because in Go you have this sequence of play where I have this position and I evaluate it and I say there's a 0.7 chance of winning, and then you play an additional stone and the model just says exactly the same thing because they're so highly correlated. Not very much on the board has changed, and so it was causing a leakage issue where it would learn from all of these highly correlated games, and then when you go and try to apply it to a new set of games, it wasn't actually doing that well. And so what they did actually is they generated a whole ton of games just from that self-play procedure from the reinforcement learning part, and then they just took a single position out of each of those games, and then they just said, do evaluation on these and try to guess from each position from those 30 million games, or one position from each of those 30 million games, predict whether they ended up winning or losing based off of this. And so the metric that they finally were able to get out of that was they were able to predict wins or losses with mean squared error of 0.234. And so that metric doesn't really tell you a whole lot. You can't reason about how good actually the value network is, but a sort of baseline is if you assume random guessing and random distribution of wins and losses, you would expect that mean squared error to be about 0.5. So it is actually doing significantly better than just random guessing. It's not getting 50% of them right, it's getting more than that. But by how much, it's kind of hard to say. So then the part that kind of combines all of this is the Monte-Carlo tree search. So this is, I would say, kind of the core contribution of all of this, is understanding how you inject the knowledge from all of these different networks into the Monte-Carlo tree search. So this is the diagram. I'll just go into more explanation on the next slide. So the first step is the reinforcement learning policy network. We'll look at the current state and it will recommend the probabilities of all of the different next moves. And so that's the network that gets 57% accuracy and has good, does a, actually no. So the supervised learning policy is the one with 57%, and the reinforcement learning policy is the one that is trained beyond that, trying to get the 1%. So the reinforcement learning policy will recommend moves basically with various different probabilities. So it says, I think this move's pretty good with 0.6, and this other move is good with 0.2, for example. And then that helps you kind of guide this Monte-Carlo tree search. And it gives you sort of a prior of which branches of play should I explore in more detail. And then beyond that, so you have your sort of first prediction, but then you want to kind of go further into the future and say, how good can my future positions beyond that first step be? So you want to look deeper into the game. And so looking at that in two different ways, you're looking at the quality of the later moves. One of the ways you can do that is with the value network. So the value network will look at the moves that are recommended and it will just try to summarize everything. And it will say, oh, well, you recommend these 8 different options basically that have reasonably high probabilities. And then the value network will look at all of them and it will say, this one looks highly winning, this one looks sort of winning, this one doesn't look like it's winning, this one looks like a definite loss, for example. And then you also combine that with the fast policy rollout. So that network I talked about at the very beginning, it's a very simple policy network. And basically what you do with that is you just sample a whole bunch of games out of that rollout network and just run it all the way to the end. So it's not a particularly strong opponent. It's not picking the strongest move every step of the way, but it is kind of simulating going through the entire game. So the value network gives you this sort of like quick evaluation, just saying, right at this position, how good do you think I am? And then the policy rollout gives you a much deeper look at all the way to the end of the game, taking somewhat reasonable moves. What do I think is going to happen? Am I going to win or am I going to lose? And then with those numbers accumulating as you're going through, it uses the upper confidence bound method that Ted has talked about in previous talks, where basically we want to explore more areas of the tree, so it's going to visit places that it hasn't been more readily. So even if it finds some move that it thinks is really winning, it's still going to continue exploring. It's not just going to continue forcing down exploration of a single branch that it thinks is promising. And so it has this internal memory of, well, I've gone down this path many different times, so maybe I go down this one and I evaluate it at least a little bit so I can get some additional confidence that this branch isn't worth continuing down. And then ultimately, I thought this part was kind of interesting. The move that it finally decides isn't picked based off of the value network or the policy rollout or any combination of those. It's purely based on how many times it visited a specific leaf. So if it, for whatever reason, just randomly decides this branch is really worth exploring and there's some other branch that it thinks is almost a guaranteed win, it's going down the branch that it visited the most often, because there might be some scenario where it only went down this branch once and it found a win, but in actuality, we want to go for the branch that had 3 wins out of 7, but we visited more often, so we know a bit more about what can possibly happen there. Do we have any questions, comments there?
That's,
So,
oh, go ahead.
yeah, can you just explain what is this Monte-Carlo tree search is, if it's okay? The basic concepts of Monte-Carlo tree search, yeah.
I'm not probably the best person to explain this. I was actually looking through all of this, and I found a 120-page PDF with a full lesson of the thing. So I don't have full grasp of it, but basically the idea is you have all of these branching possibilities, and you want to sort of simulate downstream what is going to happen, and you can't just completely exhaustively check all of the possibilities. And so you're kind of traversing this tree and trying to pick the best options and what to explore. I don't know if you have anything. Yeah.
So what I would add, just again, the short version of Monte-Carlo tree search is, I don't know how to explain it like in the super general case, but in the case of Go, it's fairly simple, right? You have 2 players and they take turns. Okay. So you can easily imagine building a tree of all the possible moves for me, and then all the possible moves in response that my opponent would make, and then all the possible, right? So as Ryan was saying, when you start at the beginning of the game with an empty board, you have like roughly 400 moves you could make, and then another 400 the opponent can make. So this tree gets enormous really fast. So what Monte Carlo tree search does is it says, okay, well, based on these other things that you have, maybe you think that these top 8 are like good candidate moves for you. And so you start with a tree that's just a root with, say, 8 branches, okay? And then you're like, okay, this is the most promising, so I'm going to explore this. And so then basically when you go down, now you've got like a level of nodes in the tree below that. So your tree starts filling out. You get some more information about that, right? And then you say, actually this other move, initial move, looks pretty good. Let me explore that. And then let's say you explore it some more and like, after simulating a bunch of games, I'm losing a bunch, and that maybe doesn't seem so good. And then you decide of all the possible things that you've looked at, what am I going to explore next? And so sometimes you might explore something near the top that you haven't explored yet, but sometimes you might be exploring 3, 4, 5, 6 levels down from your most promising branch. And basically that's what you're doing, is at each step of it, you're just saying, what's the most promising area? And it's not going to be a completely level tree, but the tree grows. And so normally what happens is you give yourself some sort of time limit. And so I would imagine when AlphaGo is playing a human, it just has a literal clock time limit, how long it's allowed to think between moves. And so when you've exhausted that, then you say, well, I've got this tree, it's pretty big. It's not like 400 by 400 branching, but it's got, maybe 700 different moves I've evaluated. Now we're going to pick whatever point in that we think is the best. And then if it's several layers down, then you actually have to walk up and say, so then my next move is the one on that branch of the tree. I don't know if does that help?
Yeah, it did help. Yeah, thanks.
I have a question. The thing is that Monte-Carlo method in mathematics, which I know, it involves jumping on in arbitrary point and exploring what happens there. And so but after many jumps, you more or less know what's going on. Is it something which happens here? Once in a while, you jumped in arbitrary place?
So the stuff that I've read, Monte Carlo tree search, I know when you hear the term Monte Carlo, you think random, but the random is not about where you choose to expand the tree. The random really just it just has to do with sort of playing things out and then backing up values from further down branches up towards the initial moves. So Monte Carlo tree search, as far as I know, is the choices you make are fairly deterministic. Okay, but there's randomness in, obviously, if I say, like, I don't know, on the screen, it looks like maybe under B, you have a choice. At the bottom, you can go to the left or to the right. You have 2 different moves P that you're choosing between, okay? The Monte Carlo part is where you say, I'm going to simulate 100 games, going to the left. I'm going to simulate 500 games, whatever, going to the right. And whichever of those 2 is better, that's my temporary estimate for the value of those 2. But it's not because the choice of left or right at that particular node was random. I'm very much evaluating what I know about the small tree I've built so far, and I'm picking the place that I want to dig further. So for Ryan's thing about the ultra fast rollout, that's where you need it, is because you don't actually want to simulate 100 games going to the left. You want to simulate ideally 10,000. And that's just for this one little expansion step.
I still don't understand what is Monte Carlo about it.
Okay, so let's just simplify this. If you were doing a 1-level tree search and it was exhaustive, okay? If I said to you, you have 300 moves you can do from here, and we're only gonna do a 1-level search, okay? So we're going to deterministically look at each of these 300 moves, and then we're going to pick which of the 300 is best. how would you evaluate how good those 300 moves are if you're not allowed to keep building the tree until the end of the game? The answer is you play 10,000 games using the rollout policy, and you use that as a sample, a 10,000 sample against the, universe of all possible games from that move. That's the Monte Carlo part.
Oh, I see. Okay.
So Ted, if I can rephrase it in my own words, it sounds like basically the Monte Carlo part is, or the Monte Carlo simulation is the part that provides you with the heuristic for an A-star search. And Hobson made a really good comment in the chat. The pruning of which branch to go down sounds very much like an A-star search. But determining the value of each of those branches is where Monte Carlo, i.e. the heuristic for the A-star search, is where the Monte Carlo comes in.
Yeah, I'm afraid I don't know A-star search. I don't know if you guys can help me or Ryan can help me, but yes, the picking of where you want to explore is not random, is based on what's most promising. But you do thousands of simulations when you do that expansion in order to do part C, the evaluation. And then the backup in step D, if you were with us for the reinforcement learning, is you're updating value estimates further up the tree in order to adjust not just how promising that most recent branch you tested is, but it also helps you get a more accurate estimate for your parent nodes, how valuable they are.
Right.
What you've described, Ted, is just A-star search. So it's it's some heuristic that you have that evaluates how good the particular branch that you went down just was.
Right. From my recollection, A-star, and it was a while since I've studied it, but A-star search basically says it gives you a couple of parameters, alpha and beta, for which branches do I ignore and which branches do I go down, right? So you would kind of say, look, when I'm evaluating these branches, if they have a value greater than, I'll pick a number, right, 0.8, then I'll explore it. But if it's less than 0.8, then I won't. So basically you're pruning branches of the tree based on some parameter that you load in. And I think what I was interpreting is, I think the way you figure out whether the value of that branch is 0.8 or 0.6 or whatever the value of that is, the Monte Carlo part, which is the heuristic that the A-star search uses to try and figure out which branches to pursue and which ones not to pursue.
Yeah, that's not normally the way you think of Monte Carlo. Monte Carlo is the random sampling part. The optimal choice of a branch, the ranking of how you're doing that sampling is that's the A-star part, or the heuristic part. So that heuristic you're talking about is a different thing than Monte Carlo. Monte Carlo just means trying to estimate a distribution by sampling it. And so by randomly sampling it, and you want to do so that's, yeah, anyway. That's my understanding.
Well, but in this case, so my understanding, Hobson, is in this case, if I'm trying to estimate the value of a particular move, right, then I would use Monte Carlo to do a tree search, or a simulation, not a tree search, a simulation of what's all the possible games that I play, what's the weighted average of all of those, so that I can figure out that this particular move has a value of 0.3, for example, right? And that is my heuristic, right?
I guess
Yeah. So yeah, I think both of you are right. So if it helps some people who aren't familiar with it, instead of calling it Monte Carlo tree search, if we called it regular tree search or A-star tree search or some other kind of, tree search that you're familiar with Monte Carlo simulation thousands of times at each leaf in order to estimate the values of a leaf. Maybe that helps people, because the tree search is normal. It's just the you're going to play thousands of games at each leaf to get a better estimate of its value. And you might start with something like the value network as your initial value for that leaf, but then when you play thousands of games, you hopefully will get a more informed estimate of how good that position is.
Yeah, thanks. This is great explanation.
I didn't realize AlphaGo was so complex, Ryan. This is cool.
Well, the later ones are simplified, so a lot of this is going to go. So I think the Monte Carlo tree search is definitely the area that I am weakest on. I specifically tried to target that with some YouTube videos and stuff, and I still feel like there's a lot that I don't fully understand about it.
Yeah, from what I read, since AlphaGo, people have been researching Monte Carlo tree search, and so they have further optimized sort of how you pick which area to expand, you know, to learn more about. And there's what is it? I'm forgetting the term now, but they've figured out ways to limit like how much you need to look and do things like that. So
so here's a visualization showing the various different pieces of that search that we were just looking at. So the first one is looking at the value network. They basically said, okay, here's the current board position. Let's just run the value network, trying every single possibility for a single move. And so you can see the value network for its favorite moves. It says, okay, this one's 50% win, 50% win, 51% win, 54% win. I think this is the best move, basically. And then, so this is looking at evaluation of just what was recommended by the policy network. This is looking at evaluation based on the rollouts, actually. So using that weak policy rollout network, it did a whole bunch of simulations, and then it said, actually, this is the one that I think is favorite. But it still thinks that this move is pretty good with 51%. And then this is the actual output from the policy network. It's saying 60%, I think you should pick this move, 35%, I think you should pick this move, 0.2, 0.3, 0.5. So these are the actual probabilities directly output from the reinforcement policy network. And then this is what it looks at in terms of simulations. So across all of these on the Monte Carlo tree search, it spent 79% going down this path, because this is what it ultimately seemed to find the most promising. And so this is what it ended up choosing. And so they used this example. This was actually, they did a show match against one of the top Go players, and he actually chose this white square that you can't really see here. And later they showed him this, and he said, oh, actually, it's more reasonable to make this move that the model is predicting. And so they also did this interesting sort of ablation looking at what happens if we just do certain subsets of that, because we have all of these intermingling parts. How strong are each of them individually and in combination with each other? And so basically they showed this is the strength, this is the ELO rating. This is the strength when we use rollouts, value network, and policy network all together. Here's what happens when we do just the rollouts and we don't do any use of the value network and the policy network. And then here's no rollouts, here's no policy network, here's all of those different combinations. So you can see all of them seem to be complementary, and it's kind of interesting it would work that way, because you kind of need that depth from the rollout going all the way to the end of the games, and the value network actually able to predict what is the quality of the move, and then the policy network able to kind of give you some guidance in what seem to be promising moves. So in question in the chat in terms of like what code is available from AlphaGo, there have been sort of open sourced versions and recreations of this, but I think that more comes in the form of the later variants. I don't think there's much for AlphaGo, because like we see on this slide, they trained it on such an obscene set of hardware that most people probably just gave up and said this isn't realistic. But the later versions, the AlphaGo 0 and AlphaZero, are potentially more manageable. So I've seen some recreations of that.
Hey, Ryan, so just a quick note, you showed 4 networks. So the supervised learning was used to initialize the reinforcement learning, but it doesn't look like it's used at all at playtime.
Yeah, so it's discarded. It's just initialization for the reinforcement learning network.
Cool.
Yeah. I see links from you, Hob, so I'll have to look at those later, but those look like good resources. Thanks for sharing. So then they have various different configurations of the network. They have the base AlphaGo, and then they have AlphaGo distributed. And so this is sort of what Ted was talking about earlier. We're just given a certain amount of time to do processing and evaluate the tree. And so on a single, not necessarily single system, but on a simpler setup with maybe a few TPUs or GPUs, you can get this performance. But then if you spread it across many different systems, you can get even more performance out of it, because you're able to evaluate the trees more deeply and evaluate more positions and get better results out of the Monte-Carlo sampling. And so this eventually gets an ELO of somewhere around 3K, which was good enough to beat the Go Pro. And so this is also looking at the performance of some of the strongest existing Go engines. And so these bottom lines, the red ones, are showing here's the performance of the free engines. And then if we give them 4 extra stones, so we basically give them 4 extra moves for free, and these are still able to beat it because it can even overcome that handicap because it's so much better than these other algorithms.
Wow.
So basically the takeaway is you're probably not doing this on your mobile phone.
Yeah. And then so the next evolution beyond AlphaGo is AlphaGo 0. And so the big breakthrough here is previously they were training on that KGS Go database. And so that had all of the play from the professional players. And now they said, well, we have this strong reinforcement learning system. What happens if we just let it try to train from scratch? It's not trying to predict professional players. It's just trying to optimize and get a model that is able to be successful in Go on its own. So they did a few things to get to that point. So they did some studies and they figured out actually a deeper network and a network with residual blocks actually does significantly better. We'll see some graphics on that later. And then they also integrated some aspects of the Monte-Carlo tree search into the training procedure. So in the previous training, in the reinforcement learning, they just directly had one system against the other. And it's just that initial policy network basically saying 0.6 this, 0.3 that, 0.1 that, and then they just sample from that in order to actually choose their moves. And it's not doing anything to look deeper at later moves. It's just directly what the policy network is able to output. And so along with that, they also eliminate the fast rollout network that we looked at previously. So they said, actually, what happens if we just make such a strong initial network that we don't have to go through that simulation all the way to end with the fast rollout network? What if we use our regular network and it's a bit slower, but we're probably going to make better informed moves, and the exploration down the tree we do is probably going to be better suited for actual strong play. So it's kind of like, I've been playing chess for a bit now, and you can sort of do the thing where you just kind of very quickly say, well, they do this and then I do that, but you don't really think about it too deeply. This is saying basically in the training procedure, let's actually try to say, like, I'm on this side, I'm going to make the best move I can. and then go back to the opponent's side and say, well, if they play their best move, what are they going to do? And then you're going back and forth all the way through the depth of the tree, basically. And so you're doing actual like professional level rollout all the way to the end, rather than that sort of amateurish random sampling rollout. And one of the very impressive things with this is they were able to beat AlphaGo with only 4 TPUs in comparison to their 176 GPUs or 48 TPUs. They had 2 different versions. One of them used GPUs and one of them used TPUs. And the new version, it's so much faster and so much more efficient that it only used a fraction of the amount of search required. So even though it has much weaker hardware, it's able to search so efficiently that it doesn't need all of the extra exploration that the other ones did. So looking at the learning curves a little bit, it looks very different from the supervised one, because the supervised one, so the x-axis here is training time and the y-axis is ELO rating. And then this blue line is the reinforcement learning. And you can see that this one starts at a much worse spot and goes up much slower than the supervised learning, because the supervised learning, it's just figuring out what do pro players make, and then it kind of reaches a certain plateau. And then that's just the best that it can do, because it's just mimicking pro players the best it can. But the reinforcement learning, it has to actually learn from scratch, where it's making tremendously bad moves. And then eventually it figures out the pattern, and it can even go beyond their previous best, which was this variation AlphaGo Lee, because it's continuing to learn and actually iterate, rather than the supervised learning that kind of stalls at whatever the human level is. And this is kind of interesting because it can go far beyond human knowledge. All of the games that we've ever played, it becomes a better strategist, better tactician. It just understands the game much better after all of this time and all of these games than anything we've ever done before. And it doesn't use any prior knowledge. It just learned all of it itself. And so along with that, you can also say, how does it do in terms of predicting professional moves? So the supervised learning, obviously, it gets to a good result, and eventually it's very good at predicting professional moves. And the reinforcement learning across the same time scale, so this is the same model, this is continuing to improve in ELO, but it's not getting any better at predicting the professional moves. So obviously it's doing something slightly different. It's not taking the same strategy as the professional player. So it's getting better, but it's not actually mimicking the pros anymore. It's done something that's qualitatively different. And then at the same time, it's also trying to predict the mean squared error or it's trying to predict the outcomes of the games. And so the supervised learning model, we saw in the previous slide, it was able to get to about 0.23 or something like that. Maybe a bit lower on this one because they've improved the network architecture that they're using. But the reinforcement learning one is able to go even further than that, and it's able to understand deeper in the game who's going to win, basically. And so you can see this one gets a mean squared error somewhere of maybe 0.17 or something like that.
So Ryan, if you go back to that previous slide, one analogy I would make to that first chart on the left, I think about like image classification, right? So the general conventional wisdom is if you had 100 billion images lying around of whatever your problem is, let's say identifying makes of cars, right? You are going to do better training from scratch on your 100 billion images of cars than taking an ImageNet pre-trained network and fine-tuning it. But that requires that you have your 100 billion images that you can, enough data to train it from scratch. And so in this case, the supervised learning, right, starts out higher. That's a little bit like, I don't know. For me, I sort of see an analogy there, right? Because because you're starting with pretty good weights when you use the pre-trained weights, but then you're sort of stuck to the vicinity of that local minimum. Whereas when you train from scratch AlphaGo Zero, it knows nothing about the game. It has to learn it completely from scratch, but then ultimately it can grow beyond the limitations of what pros know how to do.
Mhm. Yeah.
So I think another way to say is the objective is slightly different too. In the supervised learning is trying to copy a human player. In the reinforcement learning, it is just trying to beat itself. So it doesn't, the goal is different. So I think that's kind of probably playing a role here.
Yeah, and that's kind of what we see in this second graph is this is way better at predicting pros, but it's not necessarily a better player. So one of the things I kind of skimmed over in one of the earlier slides was they found value in combining the networks. So previously we had the policy network and we had the value network, and those were two separate entities, even though they had the same architecture. And what they figured out is we can combine these into a single network, and it actually shares a lot of knowledge between the two, and it creates something that's significantly stronger. So what this graph is showing is here's a dual purpose network with residual blocks is basically what this is saying. So let's do both the policy network and the value network all using one single entity. Here's doing separate with the residual block, and let's do a combined network just doing convolution with no residual. So you can see that just the addition of the residual block, they said that it gave them a boost of like 600 ELO, which is kind of fascinating because typically in computer vision stuff, the architecture stuff is interesting, but in the end, it typically doesn't seem to make a massive difference. But on this, it looks like it makes a difference of 600 ELO just having the addition of the residual connections in the network. And then this is the performance having them as two separate policy and value networks. And you can see that this is worse now. And so the interesting thing is if you, this is the actual scale of all of it combined, but if you look at the individual accuracy on certain tasks, it's actually not as good. So it does worse at actually predicting professional moves. So like if you do it as two separate policy and value, and then you just look at the policy results, the policy is actually stronger in terms of predicting pro play, but you can see that the ELO is much better. But then on the opposite side, when you combine them, its value estimation is much better. So it's much better at estimating, is this a good position or not? So somewhere in the combination between these two parts of the dual residual, it's able to get significant gains out of the ELO. Did DeepMind figure out ways to optimize the amount of computer power of the supervised learning after getting reinforced learning results? So they've definitely gotten the, so there's two different things. There's the actual like compute power that's required in order to train the model, which is one thing. And then there's also the compute power that is taken just to run the model. And so in this case, the AlphaGo Zero is actually more compute intensive on the front end in the training, but then it's less compute intensive on the back end because it's built such an efficient recommender of positions and values that it doesn't have to search as deeply. but because they put that Monte Carlo tree search in the training procedure, they made it extremely expensive during the training. One of the things that I think would have been interesting for them to do, though, is then to generate a whole ton of games using the new model and then do a supervised learning on top of that. And maybe they could have condensed it even further to say, basically, here's a superhuman player. Let's have it just play a billion games against itself and then do supervised learning against it. And then maybe you can make something that is even more efficient and condense out of there. But I don't know that they've done that. I think that's kind of an interesting avenue. So this graph is looking at the ELO improvement over time. So in the previous graphs, we've looked at one that was trained for maybe 3 days or so, and that reaches a certain level of skill that was beyond anything they had done before. But then they decided, let's train it for 40 days and see if it just continues improving and gets extremely good. And so this is their biggest model with 40 residual blocks, trained for 40 plus days, and it crosses the line of AlphaGo Master, which was one of their previous best variants. And so this is really like very far into superhuman performance, because this network down here, AlphaGo Lee, beat the world champion at Go already, and now they're so many ELO above him that it's just not even the same ballpark. And then they did some study of the ELO rating of, here's just the raw policy network, no Monte Carlo tree search, just directly sampling the moves that it outputs, and it's extremely good. It's like 3,000, so it's better than any of the other chess engines, and it's just a single inference on a single board state. So it's extremely fast, extremely powerful, and it's almost as good as their previous network that had used Monte Carlo tree search and 1,000 CPUs and however many TPUs. So it's just very interesting how much they were able to cram into there. And then there's also a massive gain when you actually combine it back with the Monte Carlo tree search. This is getting 3,000, but this is upwards of 5,000, which is just a massive gain from adding in that additional depth and exploring the game further, which is kind of interesting. You'd think that eventually this network would be so good it would just be able to directly predict the correct move, and you wouldn't have to mess with the Monte Carlo tree search, but it's still quite powerful, and in combination it's even more powerful. Any questions here? I don't know if we want to pause.
I have a quick question. I'm trying to understand this AlphaGo Zero. When it is trying to play with itself, does this mean that there are two models, like the same model, both are making moves, and then each is trying to beat each other, like the GAN model kind of stuff, and they run it in millions of them. Then you pick the best model in each round. How it is? I'm trying to understand how it is playing with itself. If some insight, that would be good.
So there's different variants in each of the different papers. So if I'm hoping I'm remembering this correctly, but one of the additions in AlphaGo Zero was they essentially made it so one agent is frozen, and then they had one learn until it beat the other one at a win rate of 55%. And then that became the new benchmark set of parameters. But it's technically one. It's not like they're training two side by side. It's just taking certain frozen checkpoints and then trying to beat them. And so I'd have to look at it, but I think in the first paper they were also talking about doing a bunch of random checkpoints from previous training iterations, trying to make sure that it wouldn't forget. So you didn't end up in some sort of degenerate case like you might with a GAN or something like that, where it just ends up getting dumber and dumber over time and just playing strategies that are successful against itself but wouldn't be successful in other scenarios. But there's a lot of detail on that in the papers themselves, but a lot of it is hidden in the sort of methods section. I was trying to focus more on the actual meat of the papers, but if it interests you, my presentation, I put the names of the papers in all of them, and you can dig through. It's kind of
this is great. I think what you explained, that kind of creates a good foundation.
Yeah.
Understand. Thanks.
Yeah, if I could add just a short thing. So the general idea of self-play is you don't have two separate things like in a GAN. It's the same network, it's the same weights or whatever. You're solving two problems really. So one is you need to play against an opponent that's similar to you. If the opponent is way too good or way too bad, then you don't learn anything because you just always win or you always lose. You get no real feedback. You need an opponent that's close-ish to your skill level. The other thing is just in general training reinforcement learning. You have problems where, you know, the model will just somehow veer off into some weird, you know, state and get stuck, or where it'll just oscillate. It won't just improve, but it'll get better and then get worse, and so then how do you know when to stop training? It's very difficult if it's oscillating. So some of those other things like periodically freezing it and whatever, those are things that aren't really fundamental to what makes it learn. They're just trying to take out these oscillations and weird, you know, issues. The main thing though is it really is playing itself. And in the simplest case, you just literally use the exact same network, you predict your move, and then use that same network, you predict your opponent's move, and then you predict your next move, and you play it out till you get to the end of the game. And if you can do this 1,000 times and you won 600, then you have a pretty good estimate that this is a 60% winning position.
Yeah, thanks. This is a great explanation.
So the last variant I'll go through today, there's other stuff beyond this, so I won't act like this is the final, but this is what we have the time to talk about, is AlphaZero. So this is, I don't know, I thought the naming was always a little bit confusing because you have AlphaGo, then you have AlphaGo 0, and then you just have AlphaZero. But the way you should think about this is them trying to extend this sort of AlphaZero framework to additional games. And so they took out the Go part, basically. And what they're trying to do is they're trying to remove all of that additional knowledge that they injected into the AlphaGo game, and they're trying to make it work for chess and shogi. And so in the previous ones we looked at, they had some handcrafted features, and they also did some exploits in terms of the board symmetry. So I mentioned earlier, they did rotations and reflections of the board because in Go, the orientation doesn't matter. The board is completely symmetrical. But in chess and shogi, that's not necessarily the case. So you can't do that same sort of augmentation trick. So they basically said, remove that. Let's see if we can still get great performance out of this regardless of that. They also slightly changed the rewards. I'd have to look in more detail about what they exactly did here because it seems kind of trivial to me to allow draws. So basically previously they were doing predictions of -1 is a loss and a 1 is a win. And then I would assume that a 0 would just be a draw and it wouldn't be a problem, but they said that they did make some slight changes in order to make it work for just generally optimizing for any expected outcome. So I guess in this framework, you could say there's 8 different outcomes. I want this one to occur, and then it would be able to optimize specifically for that. And then another thing that they took out is all of the hyperparameter optimization. So in the previous ones, they looked at all kinds of different networks and all kinds of different learning rates and different strategies and stuff. And in this one, they just said, basically, let's try to get a general framework that is strong enough that it's going to work on all of these different games, so we don't have to do any additional tuning. And so that's another one of the contributions of AlphaZero here. So one of the things that they explored along with this is the search efficiency. So they're trying to build these strong models, and they're trying to say, basically, you look at these really strong systems in chess and shogi, and they're actually just very, very fast at evaluating a whole ton of positions. And if you compare that to AlphaZero or any of the previous ones, they're actually pretty slow. They don't actually evaluate a ton of positions, but it's evaluating the ones that are valuable to look at. Like you don't want to exhaustively search everything. You just want to look at the ones that are actually viable and look like good moves. And so they were showing that in a second, AlphaZero might only look at 80,000 positions, and compare that to Stockfish, it might look at 70 million different positions, which is just a huge several orders of magnitude difference. And then you look at it and AlphaZero still just completely crushes Stockfish without looking at nearly as many moves, which is pretty interesting. Another thing that they looked at was kind of the progression of it learning book moves in chess. So in chess, there's certain openings, and chess players will just kind of learn, here's some certain variation. When you play like this, then you do that, and then you do this. And if they do this, then you do this other thing. And so this is basically just showing across training time, what moves does it seem to prefer? And it does actually learn a lot of the book openings that humans prefer. And over time, you can see that it sort of likes certain openings, and then it decides that it doesn't like them as it learns deeper strategies and stuff like that. So I guess if you're a fan of the Sicilian defense, maybe you shouldn't be using that so much, because AlphaZero doesn't like it, or the King's Indian defense. It just basically never chose to do that anywhere during its training. So it's just kind of an interesting pattern that they started looking at in order to understand, is it learning the same things as humans? And it is. It seems to agree with some of our common knowledge here. So one of the things that they talked about in this AlphaZero system is how much better they made this general learning framework, and now they can teach it in only 3 days. But this is a bit of a misleading claim, because they do it in 3 days, but they do it with 5,000 TPUs and 64-second generation TPUs. So they're able to just generate all of this super rapidly. And so it's 3 days, but it's not necessarily guaranteed to be any more computationally efficient necessarily. It is actually very good in terms of the number of steps that they're taking and the number of games that they're playing. So in the past, I've talked a little bit about sample efficiency. So how many games does it actually have to play in order to get a good result? It does well in that regard, but it's also very slow, because when it's trying to generate these games, it takes a long time, because it's incorporating this Monte-Carlo tree search that is causing it to look multiple steps ahead. And they're saying that every single move, even during the training procedure, is taking 0.4 seconds. The performance is very good, but it's also very, very expensive to run this. But the output from this, finally, after they do train it, is very impressive, because you're able to fit the entire thing on a single TPU system, and you're able to get very, very strong engine out of it. It's just very difficult to train it. So looking at the actual training results, it's kind of interesting to preview and see its comparison to other engines. So this is the scale of the Stockfish system. It's somewhere above 3,000 in terms of ELO. And you can see that AlphaZero actually, over many steps, eventually learns to beat it, but not by a very large margin, maybe 100 ELO or even less. So it's better than Stockfish, but not by a ton. And then if you look at Shogi and Elmo, which is their engine there, it's able to more significantly beat it. And so there's kind of two different angles on this. Is Elmo just worse, like it hasn't been developed for as long as Stockfish has? Or is it a case of Shogi is a more complicated game, so there's a higher ceiling for us to learn and explore beyond? And that's kind of my hypothesis here, is that we're kind of at the limit of chess skill. Maybe we can eke out additional elo, but maybe there is actually ceiling in terms of skill. But if you look at Go, this is AlphaZero eventually beating AlphaGo Zero and AlphaLee. And if we look at these, this is a system that beat a top professional, and now we're saying, okay, we can get 2000 elo beyond that. I think that it might be the case that Go is such a phenomenally complicated game that humans and previous engines just aren't very good, and there's this more significant gap and more room for it to grow and get even beyond what humans have been able to understand from it. So that's all I have today. We're 7 minutes over. I don't know if anyone has any questions, things they want me to explore or explain a little bit more. We can probably take at least one or two.
Thanks a lot. This is excellent.
Super cool, Ryan.
All right.
Yeah, it's pretty clear for me. I don't have any. I mean, we've already talked about a few different things. I don't think I have any new questions.
Thank you for taking the time to do this, Ryan. It's really interesting.
Yeah.
My only comment is, where is this 5,000 TPU system?
Well, that's the benefit that you get when you're a subsidiary of Google.
Yeah.
Yeah.
And it's kind of funny because DeepMind has actually taken some attempt at trying to separate from them. And it hasn't really gone very well, because Google is kind of like, well, we own you. So if you separate, we don't give you compute resources, and that's the end of your whole company.
Yeah, Google seems to, well, this is a whole separate conversation, but in my opinion, they're not headed in a good direction. You know, the original founders are sort of long gone. So now they're just a big corporate profit machine.
I just computed how many games should be played in a year by a person who does around average, I looked it up, average number of steps in a chess game is 25. So say a person is trying to get to the same level in 20 years. So that person should play 8,750 games in a year. Almost 900, huh? Okay.
Yeah, you're not going to beat AlphaZero, Maya.
Well, not only.
Yeah, so I'll just, one comment is that, you know, you mentioned AlphaGo Zero, they incorporated Monte-Carlo tree search in the training. So if you go back to your original AlphaGo, we talked about Monte-Carlo tree search, but that was only used at playtime. And so when all these things are saying, you know, you showed that great diagram, like, you know, one says maybe this move towards the right, one says maybe the move in the lower left corner and whatever. And then you do all this tree search and you use up your time limit, whatever it is, you know, 2 minutes or whatever. And you say, oh, okay, I'm going to make this move. That information is immediately discarded as the next move starts. And so you could see like, well, gosh, if it was really that useful for playing smarter, maybe you could have actually used that in training to actually train smarter.
Mhm.
We haven't talked about it, but sort of even harder than Go is poker. And so recently there's this Rebel paper that basically people consider it to have solved no limit Texas Hold'em poker. I think it was originally only done 2-person, but they've messed around with it. And it definitely uses Monte Carlo tree search during the training, not just at playtime.
Yeah, it's interesting that I think it kind of makes sense though, because it's similar to, like, if you play chess and you just play chess mindlessly and you don't actually sit there and try to think, why am I doing this move, or what are the additional outcomes, you're not going to improve necessarily, because you're not thinking deeply and learning from the various different situations. And I think that's kind of a similar idea here, where mindful practice is much better than kind of just random sampling of the space.
Yeah. Yeah, I think the rollout can tell you obviously bad moves.
Mhm.
Right? It's like you do this, and in 2 moves, in 3 moves, you're gonna lose a bunch of pieces, you know?
Mhm.
So that's so it'll get you that whatever moderate level of skill, you know. But
Mhm.
yeah, that like, wow, you know, even a master would not think of doing that. That is such a surprising, amazing move that pays off 10 moves later, you know. Yeah, you probably have to have Monte Carlo tree search in order to really see that. Or like the stockfish thing, or you just need to be so exhaustive in your search,
Mhm.
which you can't do for Go, you can't do for poker.
Yeah. All right, I'm gonna end the recording there. Thanks for listening, everyone.